From the equations of motion, we are going to derive equations of projectile motion. So, this object is traveling with an initial velocity u with an angle theta with the horizontal. What is a projectile? A projectile means that any object that is being projected or that is being thrown from a particular object. Every instant that this rock is going, that is moving away, acceleration due to gravity is pulling down on it. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about motion in a plane. We discussed about what vectors were and what vector components were. Now we are going to discuss a certain topic that is very interesting and very important to this particular chapter, that is projectile motion. So what exactly is a projectile motion? That is, a projectile just means that a projectile motion means movement. Now we have to understand what is a projectile. A projectile means that any object that is being projected or that is being thrown from a particular object. That is, if I have a gun, let's say this is my silly toy gun, and if I fire this particular gun, there will be a bullet flying off. There will be a bullet flying off in a straight line. But after that first initial push given by this particular gun, this particular bullet will be traveling so much that eventually it will come down onto the ground. Is it like the bullet will be going like this and immediately it will fall? No, right? The bullet will travel and then gradually fall onto the ground. And if I throw a particular rock, let's say I've taken a rock, I'm angry at my friend and I skipped a rock, or I threw a rock like this. What will happen to the rock? The rock will initially move upwards because of the initial velocity I have given it. And after some time, that particular rock will move downwards. Why? Because gravity is pulling on it downwards. So when I first threw this particular rock, what happened? So when I threw this particular rock, what happened? The rock actually moved upwards. So when I started to throw it, it initially moved upwards before reaching a maximum point. It reached a maximum point, after which it gradually fell down onto the earth. Now, why does it happen? So here, this is exactly why, this is the exact situation why we need vector components or resolution of vectors, so that we can identify how objects move in two dimensions. So, and how we can actually create equations from equations of motion. So, for now, let's focus on to the topic, that is, a projectile motion is the motion of any object that is being thrown or projected with an initial velocity that later moves under the influence of gravity alone. That is, when I throw something, initially I am giving it a velocity, initial velocity, and after some time it reaches a maximum point where all my initial velocity is being lost, and then it is traveling under the influence of gravity, where finally it will fall down to the ground. So that particular motion of an object which is thrown or which is being projected is known as a projectile motion. And in order to find out how long that particular object will go, if I throw a rock, if I fire a bullet, how long it will go, how fast it will go, not how fast, how long it will go, how high it will go, or how long it will be staying in the air for, all these can be found out using equations of motion. So from the equations of motion, we are going to derive equations of projectile motion. So from the equations of motion we learned in the second chapter, we are going to derive projectile motions equations. So the first one is time of flight. Time of flight just means that how long that particular object, that particular projectile was in the air for. If I threw something, if I shot a gun, if I projected anything onto the atmosphere, onto a plane, then how long was it in the air for before coming down to the ground? If I threw a rock, how long that particular rock was traveling before eventually hitting onto the ground. So we know first for that we need to know a certain few things, certain few elements about projectile motion. One thing you have to know is that for a projectile motion which now is represented in the x and y axes, there will be, let's say this is the origin, the path will be like this. That is, the path or trajectory traced out by the projectile will always be parabolic in nature. Always remember, the path traced out by the projectile will always be parabolic in nature, and this particular shape is known as parabola. So that particular shape will be followed by every object that is following projectile motion. Even a bullet from a gun, initially traveling a distance, it will follow that particular path. So we should know that any projectile will follow a parabolic path. Now let's assume that, okay, this is y-axis and this is x-axis. We all know that. And let's say that I have thrown something, I have projected something with an initial velocity of u. So let's say u is the initial velocity. Initial velocity is u. Final velocity will be v. V will be final velocity. Final velocity. T will be the time of flight or simply time taken. Time taken. So I'm just keeping these considerations aside. So I'm telling you that if I throw any object, it will be moving with an initial velocity v, or sorry, initial velocity u. So if I throw anything, it will be moving with an initial velocity u. Now, this is very similar to a case we just discussed prior. That is, if any vector is represented like this, then we can make it into its perpendicular and horizontal components. In this particular case, it is ux and uy. Or simply, if we dive a little bit more, we can say that this almost looks like a triangle. So, if I throw any object at an angle theta, initially I can say that it is traveling with an initial velocity u at an angle theta between the horizontal and that particular initial velocity vector. So, this object is traveling with an initial velocity u with an angle theta with the horizontal. So we can say that there will be ux and uy components, or simply, since the angle is theta, so this much is clearly understood that there will be an initial velocity vector that is u and its components will be ux and uy. So now what I'm going to do is that I'm going to consider the first equation of motion, that is v is equal to u plus at. So I'm going to consider the first equation of motion, that is v is equal to u plus at. From that, I'm going to consider only the y-axis component. Why? Because we are not going to consider the horizontal components, because only the y-axis component, that is the uy component, determines how long that particular object was in the air for. So only y component is necessary to determine how long that particular object was in the air for. We don't need to find out the x-axis component, because x-axis component is there to know how long that particular object traveled. We only need to know for what time this particular y component was there. That is how long this particular component remained in the air. So we only need the y component for this. That is, I can actually write Vy is equal to Uy plus Ay into t. Time won't have a y component for this particular derivation, so it's Ayt. And now we know one more thing, that is, here A, that is acceleration, is provided by acceleration due to gravity. That is, at every instant that this rock is going, that is moving away, acceleration due to gravity is pulling down on it. So at every point the rock is traveling, the acceleration due to gravity is pulling down on it very, very hard. So acceleration due to gravity, that is G, is acting downwards, which means here AY is actually equal to negative G. Why negative? Because it is acting downwards. So relative to the motion, the perpendicular component, that is relative to the perpendicular component Y, acceleration due to gravity is acting downwards. Hence the negative symbol, it is acting downwards. So we'll write this as Uy minus Gt. I hope that's clear. Now I'm going to do one more thing. I'm not going to consider this entire graph. I'm only going to consider the time taken for this particular rock to reach the maximum height. That is the halfway through the graph. So this point, this particular point will be halfway through the graph. So I'm only considering what is the time taken for this particular rock to reach halfway, that is midway. Why I'm doing that particular thing is because as we are moving, as this particular rock is moving upwards, it is actually moving. So as this rock is moving upwards, what actually happens is that initially the perpendicular component will be large because I'm giving it an initial velocity. Horizontal component will be same throughout this journey. So we are not worried about the horizontal component. We are only worried about the perpendicular component. So initially the horizontal component will be same throughout, and initially the perpendicular component will be changing. So it will be changing because here acceleration due to gravity is starting to pull down on it. As it grows in height, as it reaches a higher altitude, as it remains to grow in length, that is upward height, as it remains to grow in height, acceleration due to gravity is pulling on it even more stronger, which means this perpendicular component will start to reduce. It will reduce in such a manner that when it reaches a particular point, that is the maximum height point, then this vertical component will be 0. So at this particular point, there will be no vertical component because initially the vertical component was present, but acceleration due to gravity was pulling on it, and slowly the vertical component decreased in magnitude until the very midpoint, that is at the very midpoint of maximum height, the vertical component, the y component, became 0, which means if I'm taking initial velocity as u, at this very top point I'm going to take final velocity, that is vy, and as we just saw, vy is equal to 0 at that particular point. The point of maximum height, vy is 0 because acceleration due to gravity is pulling on it. Eventually the vector vy component will shrink, and at the maximum height point it will be equal to 0, which means 0 will be equal to uy minus gt. So if I rearrange this equation right now, I can write gt is equal to uy. Or this particular uy is not looking really nice. I'm going to write it in terms of trigonometry, that is retake. I'm going to write it in terms of trigonometric values, that is uy is now represented as such, right? There is an angle theta, this is initial vector u, initial velocity vector u, this is ux, and this is uy. Now if I move this uy from here to this particular side so that it becomes such, like this is the uy vector. So in order to find this opposite side, all I have to do is know the trigonometric value that opposite side will always be. That this is also a tip for you. If you have a triangle like this, always remember the x-axis component will always give you, if the angle is taken like this, the x-axis component will always be cos theta and the y-axis component will always be sin theta. That is, if we make a triangle and apply trigonometric rules, we'll always get that this base thing will always be relating to cos theta and this perpendicular component will always be relating to sin theta. So here I can write this particular uy term as u sin theta. That is, uy will be equal to u sin theta. It will be equal to u sin theta, or simply I can write gt is equal to u sin theta, or t is equal to u sin theta divided by g. Now remember, this particular equation is the time taken to reach half of the distance. This is the time taken to reach half of the distance. In order to cover full distance, all I have to do is multiply here with a 2. Then I will get the time taken to cover the entire distance. Then this will be equal to 2u sin theta divided by g. And that is the equation of time of flight. That is, time of flight of a projectile is given by the equation t is equal to 2u sin theta divided by g. So, time of flight is given by the equation 2u sin theta divided by g. So what we did here was fairly simple. That is, we first considered a graph, that is x and this is y, and we considered an object which was moving with an initial velocity, that is u, which is moving with an initial velocity u, which is making an angle theta with the horizontal. So I can write the perpendicular and horizontal components as ux and uy. Later they'll simply be u sin theta and u cos theta. Now we'll only be considering the y components here because x components will relate to the range of that particular projectile motion or how long it is traveled. We need to know how long it is staying in the air. We only need the perpendicular component. So from the first equation of motion, which is v is equal to u plus at, we are going to start and we are only going to consider the y components, and we know that acceleration here is acceleration due to gravity, and then we are going to include the values because we are only considering half the distance covered. Half of the distance covered is only being considered here, which means at this particular point, Vy will be equal to 0 because acceleration due to gravity is pulling on it. The perpendicular vector will gradually diminish and become 0 at the maximum height position. So Vy, that is final velocity, will be equal to 0, which will be equal to Uy minus Gt. Rearranging, we will get Gt is equal to Uy. We know that Uy is the perpendicular component and that means it is the sine component. So we can simply write it as Gt is equal to u sine theta, or simply t is equal to u sine theta divided by g. Now this is the halfway point. So in order to get the full distance, we're going to multiply this by 2. So we're going to multiply this by 2 on both sides. Then we will get 2t is equal to 2u sine theta by g, or simply we are going to say that entire time of flight t is equal to 2u sine theta divided by g. This is the equation to find out what is the time of flight of a particular object or projectile. So this was just an introduction to projectile motion and how we are going to find out the equations of projectile motion from the equations of motion which we learned in the previous chapter. So in the coming classes, we will discuss how we can find the maximum height and maximum range of a projectile motion and how we are taking the perpendicular and vector components. Everything will be discussed in the coming session. I hope you have understood how we take time of flight, and in the next classes we'll be discussing about maximum height and maximum reach. Thank you.